Hello, and welcome to video K1 Kinematics with Calculus for Advanced Physics. In this video, we're going to do a brief overview of the kinematics equations that you learned in physics class, except this time we're going to be looking at them from the calculus perspective. If we think about average and instantaneous velocity as a starting point, we remember that average speed is the distance traveled over time elapsed, whereas average velocity is the displacement over time elapsed. And keep in mind that the difference here is that distance depends on the path, including all of the different directions, as if you line them up in a straight line, whereas displacement is the straight line distance between the starting and the ending point. It's independent of path. So if the starting and ending point are the same, then the displacement is zero. So our distance versus displacement is, remember, the key to the differences here. Because of this, we know that speed is a scalar, meaning it has magnitude or size only, whereas velocity is a vector, meaning, of course, it has magnitude and direction. And as a result of that, we have to look at them differently and treat them differently. So if we take a look at the graphs here on the right, the first graph we have velocity in kilometers per hour of 40 kilometers per hour, and it appears to stay that way throughout the entire time that we are watching the object. So here we can easily get the average speed because the velocity has not changed, so its direction hasn't changed. We can also get the average velocity, which would in this case be the velocity of 40 kilometers per hour. In the second graph here, we can see, however, that the velocity changes quite a bit in different time portions of the object's motion. So here, when we look at the average velocity, we have to keep in mind that we have differences in displacements going on. So our average velocity of delta x over delta t is going to be x minus x naught over t minus t naught, where the naughts are our initial conditions, which, if we assume that our initial condition for time occurs at t equals 0, then our average velocity is simply x minus x naught over t. If the time elapsed gets smaller and smaller, so if rather than looking at it at 0.1 intervals, we look at it at 0.01 intervals, or 0.001 intervals, or etc., etc. As this time interval gets smaller and smaller, the average velocity becomes the instantaneous velocity, or the velocity at that particular instant. And the instantaneous speed always equals the magnitude of the instantaneous velocity, but it is not always equal to the average velocity. It's only equal to the average velocity if the velocity is constant. So as we think about moving this time interval from a large time like 0.1 hours and making it smaller and smaller, we can really think about it as saying that the velocity is the limit as delta t goes to 0 of delta x over delta t, which of course gives us dx dt. So this is our first equation here, that v is equal to dx dt. When we take a look at the graph of a particle's position versus time, the instantaneous velocity is the tangent to the curve at any point. So I could say, all right, well, what about up here at this point? The tangent is almost horizontal, so then our instantaneous velocity there is pretty darn close to 0. Whereas the average velocity is the slope of the straight line between the 2 points. This is the black line shown here between point P1 and P2. And of course, the displacement would be the difference of the positions x2 minus x1. So your delta x would be x2 minus x1. From that, we can, as I said, use the slope, find out the average velocity. You can also use a graph to determine this information for some intermediate point. Say this point Pi over here between P1 and P2. In this graph, not only is the position changing with time, but the velocity of the car is also changing with time, as you can see by the fact that the tangent at P1 is not the same as the tangent at Pi, which is not quite the same as the tangent at P2. As a result of this, changing of the velocity, the car must have an acceleration. And with this change in velocity, instantaneous velocities, we can find an average acceleration or the instantaneous acceleration, similar to what we can do for velocity using tangent lines and averages like that. So we can take our pi, we can start it close to p1, we can move it up the curve to p2 and get intermediate values of xi and ti and determine our accelerations at those points. Because of this, we keep in mind that acceleration is a vector. It depends on direction and size and speed, so it can therefore be positive or negative. But remember that there is a difference between negative acceleration and deceleration, so be careful in using those terms. Do not use them interchangeably. Negative acceleration is acceleration in the negative direction as defined by the coordinate system. And again, you can determine what your coordinate system is going to be, so you can oftentimes decide whether you want your acceleration to be negative or positive. Deceleration occurs when acceleration is in the opposite direction of the velocity. So it doesn't necessarily have to be in the negative direction. We can also look at this from a slope perspective. If we have a velocity versus time graph, then the slope is the instantaneous acceleration at t1 if we look at the slope of the tangent line here. Or we can look at the straight line between p1 and p2 here and get the slope of that, and that would be the average acceleration. And of course, the instantaneous acceleration is the average acceleration as you decrease your delta t again. So as delta t gets smaller and smaller, your instantaneous acceleration, your average acceleration becomes your instantaneous acceleration. And acceleration is the limit as delta t goes to 0 of delta v over delta t, which is dv dt. So our second way of writing one of our kinematics equations in terms of calculus. We have v is dx dt, and now a is dv dt. So now let's do some math to derive the equations that we are going to be using to explain the relationships we've been talking about in terms of having a constant acceleration. We'll get to variable acceleration shortly. But for a constant acceleration, we can say that the acceleration is k constant. So we already know that acceleration is dv dt. So if we integrate that, then the integral of dv is the integral of a dt, which means that velocity is a times the integral of dt, which is at plus some constant. Now, remember, you can find out what that constant is by saying, well, what is v at 0? Well, v at 0 we typically call v naught. So then, v is equal to at plus v naught. So there's our first equation. Now, oftentimes we want to look at this in terms of time as well, because that's what we are interested in solving for. So if we rearrange this for time, we have that time is equal to v minus v naught over a. So keep that in the back of your head as well. That's first equation. One of our second equations, well, we had said on the previous slide, or a couple of slides previous to this, that v is dx dt. Well, if v is dx dt, then dx is v dt, and I can integrate that. And I can use my equation that I just solved for as my v. So then my integral of dx becomes the integral of at plus v naught dt. So x is 1/2 at squared plus v naught t plus, again, another constant. Similar to what we did before, we say, well, what is x at 0? That is our c2. We're going to call that x naught, like we called the other one v naught. So our second equation is that x is equal to 1/2 at squared plus v naught t plus x naught. And oftentimes we don't like the x naught on the right-hand side, so we move it over and we say, well, then we end up with what x minus x naught is, and it's all of this part of the equation here. And x minus x naught, remember, is delta x. So we can then simply say that delta x is 1/2 at squared plus v naught t. Okay, so that's our second equation. Well, if we have a constant acceleration, then that means that if we draw a little picture here of our speed and time, then we have our speed on the y-axis, and we might have a couple of different speeds going on here, v naught and v, for example. And so the average speed we can find out is simply the v plus v naught over 2. Well, we said previously, and we remember from our regular physics, that delta x is average speed times time. Delta x is average velocity times time, I guess. Then we just have what our average v is. So we can rewrite this to say that delta x is equal to v plus v naught over 2 all times t. Thus, our third equation. Now, finally, to come up with our last equation that we use all the time in kinematics, we can take this last equation and we can look back way over here to the left rather, where we had solved for t, and we can substitute in that t and come up with our final equation. So then, delta x is equal to v plus v naught over 2 times v minus v naught over a. And if we simplify this out and put it into the format we're used to seeing, this then becomes v squared is equal to v naught squared plus 2a delta x. So same 4 major kinematics equations that we've used in the past, but now looking at how we get them based on calculus rather than algebra. And again, keep in mind that this is when we have constant acceleration. And this is what we dealt with in the past. However, now we are going to be looking at some situations where we are not having the nice, neat situation where acceleration is constant. Instead, we're going to have situations where acceleration is variable. When this happens, this last set of equations does not always work so well. So we again need to go to calculus to be able to create a new set of equations that allow for a variable a. So let's say this time, rather than a just equaling k, a is equal to kt, because it's varying with time. Remember, again, that a is equal to dv dt, so we can integrate this again, similar to what we did before, and now we have a as kt instead, and we end up with v is equal to 1/2 kt squared plus our constant, which we know is going to be our initial velocity, so plus v naught. Okay, so there's one equation that we're going to be using when we have variable acceleration, where k is the constant of change for our acceleration, how our acceleration is changing. Keep in mind also that to get x, remember that x is the integral of v dt. So we put this equation in for v, and we end up with x equaling 1/6 kt cubed plus v naught t, again, plus our constant, which could be x naught. Most of the time that x naught's going to be 0. But oftentimes it's not. So then we rearrange this and pull the x naught over to the other side, and we end up with our delta x equaling 1/6 kt cubed plus v naught t. So here's our second equation. Now notice these are similar to our last set of equations, but because the acceleration is changing, when we integrate that, that makes a difference to our t. And so we end up with an extra power of t going on here. And if we think about something like an object that's falling, we oftentimes like to ignore air resistance. When we do that, acceleration is just equal to gravity, so that's not a big deal. But if we don't ignore air resistance, then acceleration is also dependent on the speed at which the object is falling. So for falling objects with air resistance, we end up with an acceleration equaling gravity minus our changing speed, which would be kv. And again, keep in mind that a is equal to dv dt, just like we said previously. So dv dt then is equal to g minus kv. If we move all the v's to one side, then we get dv over g minus kv is equal to dt. We integrate both sides, and the right-hand side simply becomes time. The left-hand side looks pretty complicated, but it isn't really, and you can use your integral tables in your book to find out what that is. And the reason I'm not going to solve for this right now is because this is something that I would like you to go ahead and complete on your own to see how we go from having an acceleration of a falling object with air resistance to coming up with a time equation that's important. So I'm going to stop that there and rely on you to finish it up. However, it doesn't matter what your equation of A is, whether it's this because it's a falling object with air resistance, or if it's varying at a constant rate, or if it's linear with t or v, or with v squared or with t squared. The finding of the equations that you would need to use is the same as what we've done here. So there may be cases where you're going to be told that the acceleration is changing with v squared, and you'll have to go through the same process to find out what that does to your kinematics equations. So keep that in mind and make sure you make yourself a note that this is the video that has the process in it for when you need it. But we can summarize all of this with the following. dv equals a dt, and velocity can be written as the area under an AT curve. Or dx equals v dt, and the total displacement can be written as the area under a VT curve. And finally, A is equal to d2x dt squared, where acceleration can also be written as the second derivative of displacement with respect to time. So these three relationships are the basis for all of the math that we are going to do, and in the kinematic section, and understanding how we get this from graphs. So let's take a look at an example where we are going to be looking at an object that's moving and using a graphical analysis to determine an answer, whereas previously we would have had to use kinematics equations. A jet engine moves along an experimental track as shown here on the right. Its position as a function of time is given by the equation x equals at squared plus b, where a is 2.1 meters per second squared and b is 2.8 meters. Part A, determine the displacement of the engine during the time interval t1 equals 3 to t2 equals 5 seconds. Part B, determine the average velocity during this time interval. And Part C, determine the magnitude of the instantaneous velocity at t equals 5 seconds. You can go ahead and plug all this information into the equations and solve it. Or you can think about the relationships that we had talked about on the graph and come up with the answers with that. Either way, however, we want to treat the engine as if it were a particle. And when we treat the engine as if it were a particle, and we think about the graphical representation that we have been given, we can solve for part A, the displacement of the engine during the time interval, by simply looking at what the difference is on the y-axis between P1 and P2, so 33.6 meters. Part B asks you to determine the average velocity during this time interval. Well, the average velocity is the slope of the line that connects P1 and P2, and we can determine that to be 16.8 meters per second. And then finally, for part C, it asks to determine the magnitude of the instantaneous velocity at t equals 5. Well, the instantaneous velocity at t equals 5 is the tangent at P2, and we find that out to be 21.0 meters per second by using the slope of the tangent line there. So while we could go ahead and use all those equations that we just derived, we can also use the concepts that allowed us to derive those equations and use a graphical analysis to come up with the answers. It would have taken us much longer had we not been able to use calculus. All right, let's do another example. You are designing an airport for small planes. One of the kinds of planes that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second and can accelerate at 2 meters per second squared. Part A, if the runway is 150 meters long, can this plane reach the proper speed to take off? And part B, if not, what minimum length must the runway have? Well, let's first look at what we know. We know that x naught is 0. We know that it's going to start at rest, so v naught is 0. We know its final length that it can travel is 150 meters. And we also know that it can accelerate at a rate of 2 meters per second squared. It's always good, remember, to write down what you know and what you don't know, because as you are going along through this, some of these problems we're going to be doing get fairly complicated, so you want to keep that in mind. And so the question is, can we reach the proper speed for takeoff? So what we're really looking for is, for part A, we're looking for what is v. All right, well, we know the equation v squared equals v naught squared plus 2a delta x. Plug in our numbers and chug along. And let's see, v naught squared is 0. So 2 times 2 acceleration times 150 for delta x. This is 600. That gives us a v of 24.5 meters per second. So, is it long enough? No, it is not long enough. Part B, what is the minimum length the runway, not the railway, the runway would have to have? So now we want to know, what is delta x if our v is the minimum 27.8 meters per second? We're going to use the same equation, however we're going to solve for delta x instead. So delta x is going to be equal to v squared over 2a, because the initial velocity is still going to be 0. So 27.8 over 2 times 2 gives us 193 meters. So the runway needs to be at least 193 meters long in order for this plane to be able to take off safely. Last one. Calculate the total stopping distance of a car traveling at 50 kilometers per hour, assuming that the car can accelerate at negative 6.0 meters per second squared. Assume the reaction rate of the driver is 0.5 seconds. Well, in this particular case, we need to look at two parts of the path here. We have the car that's traveling, and they're going this way. They're going to have traveled some small distance, and then they're going to apply the brake, and then they're going to travel till they stop. So at this point, the brake occurs. At this point, your speed is 0. And here, they're still traveling the initial speed of 50 kilometers per hour. So the first thing that we want to find out, we're looking for the total stopping distance. So the first thing is, what is this part that they travel before they put on the brake? And then we want to find out what is the distance they travel while they are braking. So to find x, we can use the equation that x is equal to v naught t plus 1/2 at squared. Our initial speed is 50, but that's in kilometers per hour, and our acceleration and our time is in seconds, so we need to change that from 50 kilometers per hour to meters per second times our time of 0.5. And our acceleration at this point is going to be 0 because we are not doing anything yet. We haven't hit the brakes. When we do this, we find out that our travel time while we're reacting, our travel distance rather, while we're reacting is 6.94 meters. Now that we're braking, we want to find out how far we go there. We don't know how long it takes us to go that distance, but we do know the equation v squared equals v naught squared plus 2a delta x. So we can solve that for x, and x is equal to v squared minus v naught squared over 2a plus x naught. Now, at this point, we can either say that our x naught is 0 and we are just looking at the braking distance and then add these two together, or we can say, well, that's true, we could find out just the braking distance and x naught is 0, or we can call this the total distance traveled, and our x naught will be the distance that we traveled before we started braking. So if we do that, we save ourselves a step. So essentially, we end up with our final speed is going to be 0 minus our initial speed squared. Well, our initial speed, when we change it to meters per second, is actually 13.9. And then over 2 times our acceleration, which is -6. And then we add that to 6.94. And it turns out that the total speed, the total distance that we traveled while stopping was 23 meters. Now this is a pretty large distance. If you, next time you're out and about, look at how large, or look up how large an intersection is and see how far 23 meters is in comparative positions according to an intersection that you travel through, because this assumes dry conditions. If a road is wet, or if you as the driver or whoever is driving is distracted, these results change greatly. And the stopping distance after you apply the brakes increases with the square of speed. Look at that. Your stopping distance increases with the square of the speed. So if you're traveling twice as fast, it takes 4 times the distance to stop, which is something you really want to be thinking about when you are driving, especially when you're driving through intersections and the conditions aren't great, because if you think, oh, I got a yellow light, oh, I can just speed up a little bit and I can still get past that intersection, or you get halfway through an intersection and suddenly somebody's coming towards you, how far is it going to take for you to actually stop to avoid a crash? It's usually longer than you think. So with this video and this example, you have the ability to derive the kinematics equations you need when using calculus, no matter what the relationship is between acceleration, velocity, and time.